I have a really general question, maybe to get things started. Many years ago, when we were putting together the proposal for the MAVEN mission, we discussed ion escape in terms of 3 different ion escape processes: pickup, bulk escape, and something else. And over the course of the mission, leading up to the launch of the mission, and then after looking at the first data, we sort of abandoned that paradigm for thinking about ion escape as 3 separate processes, because ultimately Ohm's law has different electric field terms that can all act simultaneously. And an ion that's accelerated mostly by one term in one region may be accelerated more by a different term in some other region. So it's a combination of processes that can remove an ion from a planet. So we took away those, we've largely taken away those 3 separate processes. And now we just talk about ion escape as a single process that has multiple, I guess, facets to it. But in several of the presentations yesterday and today, we also hear about separate ion escape processes or ion energization processes. And I'm wondering my general question is, what's the right way to think about ion escape? Is it one thing? Is it Ohm's law that has individual terms? Or should we really be thinking about pickup as distinct from, ambipolar acceleration or something like that?
So I think, yeah, obviously, like the initial acceleration of the processes is different, and I think that's when models are really useful, and people should really start like looking at that. So, for instance, Mars is a very good example because you have a more direct interaction between the solar wind and the atmosphere. So if you start taking, the MHD outputs or hybrid outputs and start looking at those terms from the Ohm's law and really try to understand where the initial acceleration happens and what happens afterwards, then that would be great. Like obviously, when it comes to data, it's a little bit trickier because and we thought about like when thinking about ether, the idea of like going far down the tail is precisely to ignore the origin of the initial acceleration, just measure the fluxes. And the reason is because if you want to measure the different fluxes, you start coming to needing like immensely large amounts of spacecraft at different locations at different times so that you can really understand that. So I think to your question, I wouldn't abandon it because the physics are there. I think it's just like a matter of what we can do with data and what we can do with models.
Alex first.
Yeah, thanks. So I think that this is an interesting question. How do you group things? Do you group them by process or do you group them in some other way? And one way that some people have tried grouping ion outflow at Earth is in terms of heated outflow versus cold outflow. That some types of outflow processes yield flows, but not a lot of heating, so you get very cold beams, whereas other processes rely on some type of heating to create ion conic. So in the cold case, you might have a strong flow like in the polar wind, but it would be a temperature of a fraction of an EV. Whereas with the ion conic, you could have strong flows, but the temperatures could be 100 EV. And so kind of heating flow processes versus non-heating processes are one way to characterize it. I do want to point out that that Conoco has a very interesting point in the chat that we have actually a really difficult time including some of these processes in global models, and the wave heating in particular is one that we don't have a good way to predict what those wave terms are going to be. And some of the wave heating processes are due to kinetic instabilities that don't exist in things like global MHD. And So how do we predict those, and how do we incorporate those into our models in ways that aren't just putting them in with empirical heating terms is, I think, a major shortcoming of models right now. With that, I think I'll stop and let other people talk.
Okay, so Bill?
Well, following on Seki's comment and Alex's comment, from an observational point of view, Kitamura today showed that in the polar cap, oxygen isn't energized and doesn't get out. So that, and Alex pointed out that you need to add wave heating, and that happens on the auroral zone. Some time ago, I had a paper where I estimated that almost no oxygen comes out in the polar cap, and that a little bit does, and that's probably related to polar cap patches and things like that. So the action happens on auroral field lines, as what's her face from UNH showed that she was working in boundary coordinates. So perhaps the way that modelers can get to get to address where wave heating is important is to identify where the auroral zone is, and that relates to where the equatorward boundary of the aurora is, where slippage between the plasmasphere goes away. So perhaps modelers, Alex, should start to consider the plasmasphere.
Claude? Robert, please.
Bill, I'm going to disagree with you.
That's
So what
new.
else? Yeah, you forgot the cusp. Polar cap, yes, that's a different place, but there's a lot of processes that occur in the cusp, and that's where most of the dayside outflows occur. And those are on, the issue is auroral outflows are in the magnetosphere and tend to be already on closed drift paths.
We're
Right.
violently agreeing, Bob.
But the cusp goes out to the magnetopores and it escapes there. So the processes are the same. The ultimate destination, it may be different.
The point I wanted to make is, where is energy? So for large planets that are heavy,
Yes,
like the Earth, you have to add energy.
absolutely.
That has to be added in wave particle interactions.
Completely agree with that.
And it doesn't happen in the polar cap,
But it does in the cusp.
but it does in the cusp and the auroral zone. And so the suggestion I was making is that modelers focus on the auroral zone and identifying that and the limited range where wave particle interactions could occur.
Okay, thanks.
Changfei, please.
Yeah, I just share a paper in the channel which is published in a physics review letter. So it's a pretty physics-based paper. You know, I want to mention, Dave mentioned whether we can rely on generalized Ohm's law. I think the answer is yes, yes. So even when people use fully kinetic particle cell code, they can still decompose different components of the electric field into the generalized Ohm's law. Dave, you mentioned like pickup ion, right? But pickup ion, the convective electric field is also included in the Ohm's law. So I think as long as we have a generalized Ohm's law, it's possible to include more physics into a global model. Yeah, this is just my point.
Eric, please.
Yes, yeah, there was a request in the chat from Dave and seconded by Carolina to try to explain the differences between the polar cap, the cusp, and the auroral zone, and I'm going to attempt to do that. The cusp is a region that maps magnetically to the dayside magnetopause. There are two of them, one on each hemisphere. And what's unique about the cusp is that the stellar wind has direct access to the cusp. So that's it's a limited region within the ionosphere, but because that's where the energy input from the stellar wind is being focused, that's where that's where a lot of the outflow occurs. And the auroral zone is the remainder of the region that's located. It's located near the boundary between closed and open magnetic field lines, and there's some debate as to exactly where the open-closed boundary is. But this is the region where you can get energy input into the magnetosphere from processes such as substorms that occur in the tail. The polar cap is the region that is poleward of the aurora and cusp. These are field lines that are open, but they lead out the tail, so that in the absence of convection, particles on those field lines would escape. Now, there is some convection which can lead to some of the polar wind being convected into the plasma sheet. But yeah, as Bill pointed out, there's generally no negligible wave particle interactions in the cusp. It's just a region where plasma from the from high latitudes can move up, and since the field line is open down the tail, the plasma can escape.
Thanks, Eric. Would either you or another Zoom annotation savvy person be willing to annotate the whiteboard figure that I started here and sort of label the three areas?
Dave, I can't see your screen now. It's only me?
I cannot see your screen.
Yeah, it says you've started screen sharing, but you haven't actually shared the screen.
Well, that's great because my diagram is horrible. So
I guess it was censored.
yeah, let me stop share and try again. Can you see something now?
Yep, just whiteboard.
Just a whiteboard. Okay, then.
Yep, you can draw something. You're showing something, okay.
Boy, that's horrible. Okay, now someone else can annotate from there, right?
I'm not savvy with this whiteboard technology, how to do it, but yeah, there'll be a point somewhere on the day side where the connectivity of the field line switches from closing on the other hemisphere on the day side to being swept down the tail. And the cusp is the point where that transition happens.
Does anybody have Kaneko Seiki's sketch handy? That's a very good sketch to label the different regions.
Yeah, let's do that instead. Have somebody share screen.
Alex, did you show that figure in your presentation? Alex Gloster?
I didn't, but maybe I can find something similar.
Dave, but it's time. Is it okay to continue discussion or?
Well,
Let's go for 5 more minutes.
Quick Google search of magnetosphere structure image will give you that.
that'll do. That'll do. If you follow Eric, basically the cusp, the red lines here, the red part, those are field lines going into the dayside polar cap region that have just been reconnected with the interplanetary magnetic field. And this is where the strong pointing flux, particle precipitation, and all that stuff going on. As these field lines are convected to the left through reconnection, the particles get lost, and that's why you get this polar cap region where there is no real plasma there. There's a low field lines. And then as you go to the tail, they reconnect again and go back to closed field lines. And on the night side, you can't see the auroral zone, but just sort of to the high latitude part of those closed field lines, the blue there, a lot of energization processes go on that make the aurora, without going into a lot of details about what they're, but they tend to be close to the polar cap. It's sort of the just recently closed field lines tends to be the auroral zone. So I think, does that help?
Yeah, that's great.
Right. Yeah, Laura Peticolis put a link to a NASA cartoon in the chat.
So the important thing that's missing in this figure is the equatorward boundary of the auroral zone.
Correct.
And that is where the plasmasphere exists. And the plasmasphere is a real dense region, generally below 60 degrees, but it can wander all over. And wave particle interactions are important in heating oxygen on Earth to get them the 10 volts in the region between the plasmasphere, which is it doesn't show here, and the black line, which is the polar cap boundary. And that's the region where wave particle interactions occur.
Thanks. I'm using the shield of a cross-disciplinary meeting to learn stuff.
So the important thing about wave particle heating is it doesn't matter. It's not important on low mass planets, as we're finding out on Mars.
Okay, so
Right. And as Alex mentioned in his talk, it's also not so important for protons at Earth because they get out anyway. It's where it matters is when gravity is strong enough that upwelling ions do not have escape energy.
Yeah, that's, so I'm sorry I didn't raise my hand, but you know, that's what Eric said is right. I do want to point out 2 other things. One is that not all wave processes are going to heat. Some, you know, non-resonant processes like ponderomotive forces, which are present in MHD, would give you outflow without heating. But the other thing I want to bring up is that we focus a lot on the O+, but there's a number of observations of heavy molecular ions as well, and, you know, escaping, you know, out into the magnetosphere. I think Bill actually wrote a nice paper about this some years ago, looking at how that happens. But the interesting thing about the heavy molecular ions is they interact with a different part of the wave spectrum than O+ would or H+ would. And so in a way, understanding how the heavy moleculars get out also tells you something about the wave heating processes for other particles as well. So just throw that out there.
Yeah, but in order to molecular ions to get out, we first have strong upflow from low altitude ionosphere, then we got some additional wave heating, which might be preferable for heavier molecular ions, but it's a bit complicated because we need to include the upflows and outflows simultaneously. What do you think?
Yeah.
Yeah,
With molecular ions, there's also the complication of chemistry. They have a tendency to photodissociate, which is why it's rare to observe them in the magnetosphere.
yeah, I agree with that. I just think I think one of the interesting things though is you do see them though, in the outflow and in the magnetosphere, and the fact that they're there at all, I think tells you that the wave heating must be very strong, because it's hard to imagine another process that could, it's already hard to get the 10 eV for oxygen to escape. Now you need even more for NO plus or O2 plus or something like that to escape, but you do see it out there. So
yes, it's a Seki has a paper where she has some results from the ERAS satellite that she was talking about that are quite nice, and they're very good, but you need to know when the ions started, when they got the wave heating and where they got the wave heating to focus down on what's going. It's a interesting problem, and it's the Seki brought the ERAS satellite brought in the first good data set to go after it, but nobody, I guess you're chasing it. But again, this doesn't matter on light planets like Mars. So for organizing data, I guess we've decided that one of the organizing principles is small versus large planets, and that's organized by the escape energy of the dominant ion. I think, Dave, to get back to your original question.
Okay. Okay, let's wrap up the session. So thank you for talking all of speakers again, and going back to Chair and Dave for both the session.
Okay, yeah, thanks again to all the speakers, and thanks so much, Shotaro and Kaneko, for sharing the session this morning. I just have two quick announcements right now. First of all, a couple of us were having some private chat in Zoom, and I think I'm going to recommend that we make a Slack channel in the Slack workspace for jargon defined, and anyone can type into that channel, please define polar cap, and then someone who knows what that means can respond. So I'm wondering if we can set that up. And then number two, you should have gotten either an email or seen the Zoom chat or both about the poster session that's about to start. If you have questions about how to access that poster session or use it, feel free to let us know. Stephanie Vasco is here. Stephanie, do you have any sort of last minute instructions or comments about the poster session?
Nope, I would say feel free to head over there. I'll be right in the middle of the room that you land in. And if you have any questions, please let me know.
Great, thanks. So formally, we have a break for 20 minutes and then the poster session starts. But of course, if you wander in there immediately, some of us will be in there starting 2 or 3 minutes from now. And the poster session will go for 2 hours. And after that, there's no formal getting back together. We will just see you again at 7 a.m. Colorado time tomorrow. And thanks again for participating. And it was great talks and discussion.